In this video, we're going to look at neutralization reactions. A neutralization is what you might guess. It's the reaction of an acid and a base. One of the products will always be water, and the other product is always some kind of a salt. And by salt, we just mean anything ionic. It doesn't have to be sodium chloride table salt. And so a good example would be something like our traditional HCl plus sodium hydroxide. Pretty typical strong acid and strong base. It's basically it's really a double replacement where you've got two compounds, plus one on the hydrogen, minus one on the chlorine, plus one, minus one, and we're just going to switch the light charged ions. So I could bring sodium with chlorine, and then a hydrogen with hydroxide. And because everything is plus one or minus one, I know that my products are already neutral. So in this case, the salt actually is sodium chloride, and then your HOH is also known as water. Hydrogen hydroxide, another name for water. So there's always somebody that'll ask, like, if I put hydrochloric acid and sodium hydroxide in my mouth at the same time and I like swirl it around or gargle it, you are kind of gargling salt water. Now, I wouldn't try that. You'd have to have like equal molar solutions and equal volumes so that you have the perfect one-to-one stoichiometric ratio of acid to base so that you really just get salt and water. If anything was off, if you had anything limiting or excess, that might not end so well for you. So I've never tried that. I don't really plan on it. It really can be any acid and base. It doesn't have to be hydrochloric acid and sodium hydroxide. We could do something like hydrochloric acid. And what if I switch up the base? What if I make it something like calcium hydroxide, where this is a plus one, minus one on the hydrogen and chlorine. Calcium is a plus two, minus one. I would need two hydroxide. It's still an acid, it's still a base, it's still a double replacement, but now I would get calcium with chlorine and hydrogen with hydroxide. My calcium was plus 2 and my chlorine minus 1, so I need to fix that one a little bit. But then this should be fine. It's plus 1, minus 1, which I didn't write the charges in up here. If that bothers you, I could do that. It's all neutral. Now, the first one, everything was a 1-to-1 ratio. The second one, I'm going to have to balance. I'm going to eventually need 2 hydroxide on the product side. So here's my 2 hydroxide. Now I need 2 hydrogen. Got to go 2 on the hydrogen. And then 2 chlorine, 2 chlorine. Perfect. The thing to recognize is just that I want to treat the hydrogen and hydroxide as 2 ions. So when I look at that 2 water at the end, I think of it in my head as 2 hydrogen ions and then 2 hydroxide, even though I could really write it as H2O as well. It's 2 waters. Here would be some real typical examples of a neutralization. An acid plus a base, you get water and then something ionic. It doesn't have to be sodium chloride. It could be calcium chloride. It could be any ionic compound. All right, cool. So in the laboratory, we're going to do some neutralizations using a method called a titration. A titration is a method of mixing an acid and a base. Usually there's one solution of known concentration and one solution of unknown concentration. And it could be that the acid or the base, it doesn't matter which one we know and which one we don't know. But by using the ratio in the balanced equation, we can figure out the concentration of the unknown acid or base. It's really the S word. It's going to be some stoichiometry. You're going to love it. But this method, this laboratory method, is called a titration. And the idea is that we're going to mix the acid and the base until we hit something called an equivalence point. And when you see the term equivalence, it makes you think that something is equal, equivalent, something must be equal. Yes. The equivalence point is when our moles of acid and base equal the ratio from the balanced equation. Here it says the moles of acid and base match the ratio from the balanced equation. They match, they equal the ratio from the balanced equation, the equivalence point. Oh, fabulous. That's like the equal part, that we mix the acid and the base until we hit the ratio from the balanced equation. Then we stop the titration. We stop mixing them. So if I had hydrochloric acid and sodium hydroxide, I would mix them together until I have a 1-to-1 ratio of moles. If I have hydrochloric acid and calcium hydroxide, I'm going to mix them together until I have a 2-to-1 ratio of moles. And then I stop. Well, how do you know when to stop? I mean, if all you're making is a salt and water, how do you know when you've got the ratio in the balanced equation? Well, one thing that we look at is the pH. If I'm mixing a strong acid and a strong base, which these equations both are, they're strong acid and strong base. When you hit the equivalence point, the final solution should be totally neutral. Because in both of these examples, look at what's produced. Sodium chloride and calcium chloride are neither acid nor base. They don't have hydroxide. They don't have hydrogen. They're totally neutral. And then your hydrogen and hydroxide join up to make water. So even though I start with an acid and a base, on the product side, everything is neutral. The salt is neutral and water is neutral. The hydrogen and hydroxide join to make a neutral molecule of water. So one thing we look at is the pH. If I start with an acid, the pH will be pretty low. Well, then as I add the base, I'm going to stop when my pH is 7. Cool. We could also say the same thing about weak acid, weak base. If I were mixing a weak acid and a weak base, I mean, neither of them produce a significant amount of hydrogen or hydroxide. In the end, the products should be pretty neutral. Where things get a little bit crazy is in the middle. Let's say I mix a weak acid and a strong base, and I want to stop at the stoichiometric ratio in the balanced equation. Well, just because of the nature of the particle, your final solution may not be neutral. For example, if I had the stoichiometric ratio in the balanced equation, but the acid was weak and the base is strong, let's pretend it's a 1-to-1 ratio even. I have a 1-to-1 ratio of weak acid and strong base. The problem is the strong base dissociates fully and produces all this hydroxide, but the weak acid just does not dissociate fully. And so the acid doesn't give off as much hydrogen as the base gives off in hydroxide. So even though you look at your balanced equation and it looks like it's a perfect 1-to-1 stoichiometric ratio, the products might not be neutral. And in fact, we'd expect them to be slightly basic. And it's just the nature of the particle that the base will dissociate fully until you'll get all this hydroxide, but the acid will not dissociate fully, and so you won't get enough hydrogen to match up with all the hydroxide from the base. Kind of the opposite happens if I use a strong acid and a weak base. The strong acid would dissociate fully, so you'd have all this hydrogen in your solution, but the weak base would not give off as much hydroxide. So I could have the stoichiometric ratio in the balanced equation, but the final solution might still be a little acidic. And so here we're estimating like a pH of 9 or 5. in a nutshell, really, if I have a stronger base and a weaker acid, I'm just looking for something greater than 7. Or if the pH, or I should say, if the acid is strong and the base is weak, I'm just looking for a pH less than 7. I mean, it could be a 6.5, maybe a 4. I guess it just depends on how much the acid and the base dissociate. And so that's one of the things that we look at to know when to stop the titration. We look at the nature of the acid and the base. Are they strong? Are they weak? And what pH range them am I looking for when I have equal moles according to the ratio in the balanced equation? The setup of your titration will look like this. We're going to have this big glass tube called a burette. The burette has markings for volume. The burette could contain the acid or the base, but in general, it's always the solution of known concentration. This is the solution of known concentration. It could be acid or base. It doesn't matter. But one of them you always know the molarity, and the other one you're trying to figure out. The known solution goes in the burette. Down in the bottom, you'll have your acid or base. But the main thing to know is that this is the solution of unknown concentration. This is your unknown. That goes down in the flask. There's a little valve on the burette called a stopcock, and that's what we can use to then transfer very specific volumes of the known solution into the unknown. In the end, we're going to want to know how much volume it took to reach this equivalence point. That's the point where I had the stoichiometric ratio from the balanced equation, and I stopped the titration. I stopped mixing my acid and base. And so we just said that one of the ways that we know when to stop is by looking at the pH range. That if I have a strong acid and a strong base, I'm expecting that final solution to be neutral when I'm at the equivalence point. If the acid is strong and the base is weak, then I'm looking for the pH to be something slightly acidic, even though I have the stoichiometric ratio from the balanced equation. But when you really start thinking about it, like how do you get the pH? Like how do you know the pH of this final solution? I mean, do you just like throw little pH strips in there? Or I guess you could. In the lab, we could use a pH probe. We could put like a little pH probe in there, kind of like a temperature probe, but it measures the change in pH. That works fabulous. Or we often use something called an acid-base indicator. Acid-base indicators are solutions, and usually they're like weak acids or weak bases themselves. But the cool thing is that they turn different colors depending on the pH. And so if I know that I want my solution to be neutral, it's a strong acid, strong base, I'm going to mix them together until the final pH is 7, neutral. We could just pick an acid-base indicator that turns a specific color when the pH is 7. And so then I don't have to like keep testing with pH strips, like, oh gosh, it's not 7 yet. We might know, well, this indicator turns green when the pH is 7. So I just keep mixing until the solution turns green. Then I stop. That indicator then will be added to the flask. Flask, beaker, we usually use a flask, but it could be either. The flask will get the unknown solution and the indicator. The known solution, known concentration, that goes up in the burette. And that we're going to measure very specifically how much volume is delivered in order to reach this equivalence point. So here's a list of common indicators. And now this looks a lot prettier when it's in color. In your study guide, it's unfortunately black and white. But here are some common indicators. Now, I might have my favorites, but here's what they look like. If I were titrating a strong acid and a strong base, and I know I want something then that's going to turn colors at a pH of 7. My favorite is this guy, the bromothionyl blue. And this is up on top, it'll say, for strong acid and strong base. That methyl red, I don't know about that one. I want something that turns colors at a 7. And I would never use this one. That one makes me nervous. This one, smiley face. I always use bromothionyl blue. I love it. It gives me a great color change. If you start with that bromothionyl blue in an acid where the pH might be like 4 or 5, it's a very distinct yellow color. Then you start mixing in, let's say you start adding base. Well, eventually the pH starts to increase. And if you're titrating a strong acid and a strong base, you stop at green. So it's going to start out yellow. When it's green, you stop. That would be the pH 7. Look at that. It's perfect. 7. That's why I'd stop the titration. If you add too much base and the pH goes beyond 7, it turns blue. And then you know, we got to start over. We got to run this one again. We went too far. We'll say that you overshot your equivalence point. But I like that bromothionyl blue. The colors are really easy to see. Yellow, green, blue. I want to stop at green. That'll indicate that I'm neutral, which would be the equivalence point in a strong acid, strong base titration. If I'm titrating a stronger acid and a weaker base, either of these are fine. Methyl orange, bromophenol blue, but I kind of like this one better. Methyl orange. I think the colors are just a little easier to see. So methyl orange will change colors in this pH range of like a 3 to 4, which is about what I'm looking for. If the acid is stronger, the acid will dissociate more fully than a weak base. And so even though I might have the equivalence point, I might have the ratio in the balanced equation, the final solution just won't end up being neutral. It'll still be slightly acidic. Both of these indicators turn colors in a slightly acidic range, so they're both fine. But I just feel like this one's a little easier to see the range of colors. When it's really acidic, it starts off red. So like pH 1, 2. And then when it's like mildly acidic, right in the middle, like around 4-ish, it'll turn orange. That's when you'd stop the titration. If you go too far, it'll turn yellow. And in this case, too far might be a pH of 7. That if it's strong acid, strong base, at the equivalence point, it should still be slightly acidic, not neutral. I just think these colors are a little easier to see. The bromophenol blue, it's weird, it never really turns blue. It kind of goes like yellow, pink, and then like a purpley color. I just like this one better. And then finally, here are some options if you're titrating a weak acid and a stronger base. And where now the base is going to dissociate more fully than the acid. And even though I might have the stoichiometric ratio in the balanced equation, my final solution will still end up slightly basic. Of these, the one that we use more often is probably the phenolphthalein. And again, they're both fine, but we'll use phenolphthalein in the lab. So I might give this one my smiley. And you've probably used this one before. When the solution is acidic, it's crystal clear. And then right around like a pH of 8 or 9, it turns like really pale pink. So it starts off clear. And this is a super light pink, pale pink. Like cotton candy pink. If you go too far and it goes like super basic, now it's like a dark pink. We're going to use this one in the lab, and it's so easy to tell when you've gone too far. We want the solution to be slightly basic, but I don't want like an 11, 12, 13, 14. And sometimes it really might be like one drop, where you're like, oh, it's kind of pink, but let's just add one more drop. And you add one more drop, and boom, it's dark pink. I mean, it's a beautiful color, but it's too far. And then you'd want to start your titration over. So, and we're going to use a couple of these indicators in the lab, and they'll help you to visualize when to stop the titration. We want to stop the titration in the correct pH range, depending on what type of acid and base we're using, and these indicators should then turn colors at that appropriate pH range.